this mechanical universe. If you search mechanical universe special relativity, you can find the movie and stream it free online. And one thing we learned in the movie was that, and also it's in your book, that if you measure the mass of something moving at relativistic speeds, you will measure a mass greater than what it had at rest. And that's a common occurrence at the particle accelerator at Stanford. And so the equation you would use to figure out the mass is this. It looks more like the time dilation equation because mass is increasing like time is, whereas length gets less. And so these electrons are accelerated by having a positive charge in front, a negative charge behind, and those switch as it moves, so it's always being pulled from in front and repelled from behind, and it'll go really fast and hit something, send stuff flying. How fast? Really close to the speed of light. And so we can use conservation of momentum to get the mass of the electron. And at that speed, we would find out that its mass by adding up all the momenta of the pieces that went flying, just doing a conservation of momentum equation like we did in class, that the mass of the electron is 2,236 times the rest mass of an electron. That's more than the mass of a proton. And so there's using the equation to confirm that. Where did that mass come from? Well, we're putting energy into the electron. And so it came from PG&E. Stanford had to pay for that. Well, the energy lab anyway. And so you can take energy and convert it to mass, and you can turn mass into energy. And if you look at the equation, Einstein's equation, we can show this equivalence. And so the mass is E over c squared. And so E is a Newton meter, and c squared would be meter squared over second squared. Put in newtons into here, and you should be able to show that comes out to kilograms. It'd be a good exercise for you to go through. And so here's some examples of mass energy equivalence. Here we convert energy into mass. Two gamma rays can slam in each other and disappear and create a positron and an electron. Positron is the antimatter component of an electron. So before we didn't have any mass, we just had energy, and now we have two particles with mass. Also a chemical reaction that's endothermic. That is, you have to put energy in for the reaction to occur. That's why a cold pack would feel cold. And so the mass of the products would be more than the mass of the reactants. But it's so small, you usually ignore that and just use, say that the mass is the same, but it's technically not. How about mass to energy? Fusion and fission reactions. If you add up the mass of the helium created by fusing hydrogen in the hydrogen bomb, you'll find out that there's less mass than you started with, and that was converted into energy, which is enough to destroy an entire city. In a nuclear reactor, you're splitting uranium, and if you add up the mass of the particles afterwards, it's less than the uranium atoms you split. And so some mass is converted to energy. And also an exothermic reaction, you're releasing energy, and so the mass of the products is going to be less than the mass of the reactants. But again, so tiny, it's usually ignored, but it does happen. And here's a question. Consider a motorcycle powered with super powerful electric batteries and a common electric streetcar. Well, it wouldn't be very common if it's going at a speed approaching that of light. And so we measured their masses before they started going, and now we're going to have them zoom over a scale and measure their weight and then calculate their mass. Which one would go up? I'll pause it and think. Okay, you're back. It is only the streetcar. The streetcar is like the electron in slack. The energy is coming from outside and being converted into mass. But the energy that the motorcycle's using was in the batteries. And so we are just taking chemical energy stored in the batteries and converting it into kinetic energy. And so as the mass goes up from the speed, the mass in the battery goes down, and so there's no net increase. And we talked about going faster than light. Well, you can look at the equations for special relativity, and it sure looks like if you put v equals c, that it's just not going to work. But maybe that's a flaw with the equations. If you look at the mass one, you can see at least why it's going to be really hard, because if the mass is going up to an infinite mass, you're going to need an infinite force to have an acceleration so you can keep increasing your speed. But here's another way to think about it. I have a runner, and she can always add 10 miles per hour to her speed. And she happens to be on a rocket ship that's very long, so she can keep running. And it's going 87% the speed of light. So she decides to speed up by 10 miles per hour. How much faster is she going from our perspective? Well, that 10 miles that she might go in an hour would only be 5 miles to us. And the time, instead of being 1 hour, would be 2 hours. So she only added 2.5 miles per hour. Well, if she were to add another 10 miles an hour, this would be less than 5, because she's going 0.87c plus 10 miles an hour, or plus 2.5 miles per hour. And then the time is going to be more. And so every time she adds some speed, the space contracts and time dilates. And speed is space over time, and so the numerator keeps shrinking, the denominator keeps growing. So she can go faster, but she never quite gets there. So it's kind of like something called Zeno's paradox. Look it up. And so she's never going to get there. But maybe there's other things we could do. What if I have a spaceship going 0.8 and it launches a missile that can go 0.4? Wouldn't that be going 1.2 times the speed of light? Or how about two spaceships approaching each other at 0.8? Wouldn't that be going at 1.6? But the speeds don't add according to Galileo, because these are going fast enough to have noticeable contraction of space, dilation of time, and so you need to use this equation. You could find a derivation of this. It's not real simple, but notice that if the speeds are small, this term is essentially 0, and so you just get vrel as v1 plus v2. But if they're not, like in this case here, I get 0.976c. And for the, so if you look, vrel is never going to be equal to or greater than c, if whatever you put in here, as long as it's less than 1. What would be the velocity of the missile relative to us? 0.8 for this rocket ship, 0.4 for the missile. See if you can use this equation and figure it out. I'll give you the answer. Pause it. It's that. And so that concludes our look at special relativity.